When we think of magnets, we usually think of a fridge decoration or compass. But in greater physics, magnetism isn't just a property of certain metals, it's a dynamic vector field. We can call this the magnetic field, represented by the capital variable B. Because it's a vector field, it has both magnitude and direction. By absolute physics convention, magnetic field lines always exit through the North Pole and enter the South Pole. If you look closely at the screen, notice how tightly packed the lines are right at the tips of the poles, compared to how spread out they are in the middle. This spacing tells you the field's intensity. Dense lines mean a high field strength, measured in Teslas. For a long time, scientists thought electricity and magnetism were completely separate, but they aren't. Magnetism is actually just a byproduct of moving electrical charges. Whenever an electric current flows through a conductor, a magnetic field instantly generated around it. To determine the shape and direction of this field, use our first core visual tool, the right-hand rule for a straight conductor. Imagine gripping the wire with your right hand. If you point your right thumb in the direction of the conventional current, your fingers naturally curl in the direction of the magnetic field loops wrapping around the wire. If we reverse the current direction, the thumbs point down and the loops instantly reverse. It is a direct causal link. Now let's look at the most trickiest and conceptual part of this unit. What happens when an isolated moving charge enters an external magnetic field? On screen, these X marks represent a uniform magnetic field pointing straight into the page, away from you. Imagine looking at the feathers of an arrow flying away. Now let's launch a positive charge horizontally into this field. The moment that moving charge enters the field, it experiences a deflecting physical force known as the Lorentz force, or Fm. To find its direction, we use the right-hand rule for force. Point your fingers into the screen with magnetic field. Point your thumb to the right of the velocity of the charge, and your palm pushes upward, the direction of the force. To find the exact magnitude of this force, we use the core physics equation, Fm equals Q times V times B times sine of theta. Let's break down the variables now. So F of m is the magnetic force in newtons, Q is the charge of the particle in coulombs, V is the velocity of the particle in meters per second, B is the magnetic field strength in teslas, and theta is the angle between the velocity vector and the magnetic field lines. Because our particle is moving horizontally and the field is pointing straight into the screen, the angle between them is exactly 90 degrees. Since the sine of 90 degrees is equal to 1, the force is at its absolute maximum, perfectly deflecting the particle into a circular path. This isn't just theoretical math, it's the exact reason life exists on Earth. Our planet's molten iron core creates a massive magnetic field called the magnetosphere. At the same time, the sun constantly blasts out solar winds, a stream of highly energetic, fast-moving particles. If these particles hit our Earth directly, they would strip away our atmosphere and destroy our DNA. But look at the physics. As those charged particles Q fly towards us at high velocity V, they strike the Earth's magnetic field B. The Lorentz force, F of m, takes over, deflecting the dangerous particles harmlessly away from the equator and guiding them towards the north and south poles. When these particles collide with our upper atmosphere at the poles, they light up, creating the aurora borealis, the northern lights. It's a literal planetary shield driven by the Lorentz force. To wrap up everything, magnetic fields are directional vectors that flow from north to south. They are generated by moving charges, which we map using our right-hand rules. And when external fields and moving charges interact, the resulting Lorentz force alters the path of particles, mathematically governed by F of m equals q times v times b times sine of theta. Thank you for watching this breakdown of magnetism in physics. Good luck on your exam review.